So this was some work I did a few years ago with David Hogg, who's in the audience here, and also Rebecca Oppenheimer and Doug Brenner, who are at the American Museum of Natural History. So, the work I'm going to describe, most of it came out in a journal paper in the Astrophysical Journal. And this was really concerned with basically one particular planetary system that's particularly interesting and looking at the spectrographic composition of the atmospheres of these planets around this particular star. Now, of course, exoplanets is a super hot field. There's been a huge number of new results since this paper came out. And so what I'm really going to focus on my talk today is really the method and the techniques rather than the actual results themselves, because they've been surpassed by new instruments that have come online and so on and so forth. Okay, so just to talk for a moment here about direct imaging. So there's many different ways of finding exoplanets. This talk is solely concerned with direct imaging, where you essentially point a very large telescope at a nearby star and try and look for companions. And even though it's much more difficult to find the planets than other techniques, there's a very sort of clear benefit, which is that you can determine the composition of the atmosphere of the planet. So this is one of the few methods that can do that. So I wasn't actually aware that any other method could do it until the previous talk, when I saw that the transiting methods can also kind of get at this kind of information as well. And of course, what we're ultimately what we're looking for would be some signature of various interesting molecules in the atmosphere that might indicate some sort of organic compounds or even life. Okay, now one of the challenges, of course, is when you point the telescope at the star, the point is that the starlight, of course, the star is massively brighter than the planet, and somehow you've got to be able to remove the starlight and leave just the light that comes from the planet. So there's a really sort of a big problem here is the sort of contrast issue. And so just to detect Earth-like planets surrounded by stars, you need to sort of be able to handle contrast ratios of about 10 to the 7, and if you want to get the spectrum out, it's 10 to the 9 or 10 to the 10. And that's currently, for Earth-like planets, that's currently, these are the ratios. That's probably beyond what we can do currently, but there's lots of new devices coming online, in the future that might be able to access that. So anyway, this work was done using. Okay, so for some reason my slides seem to go slightly off the top of the screen there. So this was called Project 1640, where Rebecca Oppenheimer was the PI. So this was using the Hale telescope at Palomar, which is, I guess, a pretty big telescope, not as big as the latest ones. And on the back of this giant telescope was a coronagraph. And so the basic principle is to have a kind of mask, basically, which blocks out light from the star. It's like a sort of just like you have the sun shield in your car. So it blocks out the sun, and you can hopefully then see the light from the planet. And this is, actually, there's a mask, but then there's a very complicated, sort of optical train, essentially, which takes the light coming in from there's an adaptive optics system that's running on the back of that telescope that goes in, and then the little mask is here, and then they have the camera sensor is over here. So this is a near-infrared camera. And it also records simultaneously over about sort of 32 different wavelengths. And so when you take the images, this is what the resulting thing looks like. So in the center, you're looking at you can see the dark spot is the region that's been masked in the optical train. These funny artifacts you're seeing, these are essentially diffraction artifacts that people often call speckles. And because diffraction, of course, is wavelength dependent, so what I'm doing in this little animation here is playing through the through the different wavelengths, and you can see that the noise pattern due to this diffraction moves in a radial fashion. And that I've chosen this example because you can see here that there is a planet, or an exoplanet rather, that is actually stationary. So the point is the planets don't move, but the structured noise does as a function of wavelength. And so the question, of course, this is a ground-based telescope, so when we take two different exposures of that star, then of course the atmosphere has changed slightly. There'll be different sort of, maybe the star's in a different location in the sky depending on the time of night. And so, you end up with basically slightly different diffraction patterns arising. Okay, and if you're in space, a lot of these problems go away. But for a lot of these, this particular instrument is on the ground, and quite a few of these direct imaging instruments are on ground-based telescopes. And so what I'm going to talk about is actually just one particular star, just because it's using this as an example. So this is a particularly interesting one because it's close by. It has a series of companions that are assigned the letters A, B, C, D, E. They're all fairly large, and they're young, which means they're hot, which means the planet is radiating quite strongly in infrared, and then you're sort of seeing that signature, the infrared black body radiation curve is being attenuated by the molecules in the atmosphere of the planet. Okay, and that's hopefully, so if we can measure the spectra and we know the black body radiation, we can try and figure out where the dips in the spectra would correspond to different molecules that are in the atmosphere. Okay, so the first thing I want to talk about is just trying to find the planet, and then we'll talk about how we're going to characterize the spectrum. And the algorithm that I came up with was called spatiospectral speckle suppression, which is a bit of a mouthful, so we just abbreviated it to something called S4. And so that's actually detailed in a separate journal paper that followed on from the main science discovery paper. Okay, so the basic sort of mindset here is, instead of trying to model that very complicated optical train I just showed you, which obviously it's incredibly sensitive to any perturbations in the train, for example, as the telescope moves around. Instead, we're just going to use a whole series of exposures to build a statistical model of what that speckle noise looks like. But one of the challenges really is that for any given star, that speckle pattern does change quite a bit, and we won't have too many exposures. It takes quite a while. The exposure times are quite long. Observing time, of course, is fairly limited. So you typically have about a dozen or so exposures at most to work from. And so basically, what we're going to try and do is to use the sort of the structure of the problem to try and create more examples from which we can build a statistical model. So the first thing we're going to do is to try and pick a representation in which it's sort of easy to build a model. Okay, and so I think this is a general lesson when you're applying sort of learning techniques. If you can pick an appropriate kind of input representation for the model, it's going to make life an awful lot easier for you. So what we do is that we take advantage of the fact you have this radial motion of the speckles that I just showed you, and what we're going to do is to operate in the polar domain. So what we've done here is to take a little annulus at a certain radius and a certain thickness r, and we're going to just sort of remap that into now this sort of, this is the angle here, this is the little radial strip, and of course we have a wavelength direction, which is the third dimension here, which sort of goes in, and if you take a little slice here, what you'll see is, sorry, let me just wind back a second. So the point is, in this representation, the speckle noise moves horizontally, okay, now, because it's moving in a purely radial direction. It doesn't change the angle. And then if we take a slice, so it's sort of in the third dimension, sort of into the wavelength, and just look at what we've got here. So this is an example just of a position where there is no companion or planet. Then what you see here is these diagonal structures. This is the speckles moving kind of radially. And if you take this is a location where there was a companion, so this is one, quite a bright one that you can just see easily with your eye. And you can see this is superimposed as a vertical structure. Okay, so it's a question of separating the sort of diagonal structure from the vertical structure to separate out the planet from the speckled noise. Okay, so what we're going to do is essentially when we're probing a certain location, what we're going to do is to sort of divide this strip into kind of a train and test region. Okay, so we're going to have a little the held out region in red, where we're going to sort of check to see whether a particular planet is located. And we'll use the remaining parts of that annulus to be the training set for our model. And the idea is we're going to sort of course, exhaustively probe all possible radii and angle positions. Okay, so we'll, in the next we'll build a model for this region in red, evaluate the model on it, and see if it gives us a sort of detection result, and then we'll move that red region down, and then repeat the process. Okay, so. And the advantage of doing this is that this is actually a sort of key thing because we don't have that much data. So when we're building this model of the background noise, we're assuming, of course, that in this green region there is no companion. Okay, so this is sort of assuming that at a given orbital radius there's only one possible body orbiting the star, which I think is a reasonable thing to make to a first approximation. So when we do this, essentially the data matrix that we end up using is going to basically have the number of samples will be the number of angles we have at a particular radius minus that held out zone, and then times the number of exposures we have, which would be roughly a dozen. And then in the sort of each sample essentially is then we'll have a dimensionality which is the product of the annulus width, say roughly 20 pixels, the 30 wavelengths, and then we have some little bit of width in angle, okay, because those speckles aren't just confined to a single row, as it were, in that strip. They do have some width. Okay, so we take this matrix here. Now, the simplest possible, model of the data you could think of building, it would be something like PCA. Okay, so we're going to start just with doing that. And so if you do that, this is your little sort of speckled basis, if you like, and we're just showing the different, basis functions here. This is, a linear representation that we built of that data matrix. And we're just showing the spectrum here. And you can see this, the energy of the different principal components drops off fairly rapidly. And in practice, we're going to be using, say 20 to 30 principal components. And that you can see by that point, we captured most of the energy. And so the simplest, we're going to start with the simplest thing you can imagine, which is just to essentially just try to reconstruct each test region in this PCA basis. So when you do that, here's a region, here's your PCA reconstruction using 20 principal components, and there's your residual. Okay, so these are not on the same, sorry, this right-hand one here is on a different intensity scale. I'm sort of increasing the contrast so you can see this thing. Now, the point being, the simplest thing you could do is to try and, if you do have a companion and you fit this PCA basis, well, the idea is that the PCA basis really, as you saw, sort of models the diagonal structures very well, but it's going to struggle to fit the vertical structure that results from the companion. Okay, so when you do that, your reconstruction looks sort of okay, but not great. And then, of course, you see that in the residual there is actually some structure left. It's not just some sort of residual Gaussian noise or anything like that. And what you can then do is to sort of, essentially take your assume some model of the planet, okay, which would be, say, you have a known PSF that you can measure on the telescope. To start with, we're just going to do a very naive assumption that the spectrum of that companion is white once you've calibrated the instrument and so on. And what you could then do is just simply correlate this residual with your planetary model. Okay, this is a sort of order 0 approach to doing it. And the idea is that somehow, when you have a residual that looks like this, you should get some high response. And when you have one that looks like that, you should get some low response. Okay, so if you do this on these stars, I should also point, this is actually, the algorithm I've just described is, up to sort of minor details, very similar to some of these sort of existing other ones out there, particularly this CLIP approach that's used quite widely as well for direct imaging processing pipelines. So most of these approaches have this idea of trying to fit some model and just look at the residuals. So if you do that, I'm just comparing, this is the CLIP approach, this is R1. These are the kind of residual maps you get left after you've done the PCA fitting at each location. So if you see a sort of white spot, this is just summing the residual error over wavelengths. So you see sort of bright spots essentially at different positions where you think there might be a companion. And then in our approach, we sort of then do a sort of correlation with this matched filter, if you like, of the planetary model. Okay, and you should get, the color scale here, red is high, so you get sort of bright spots where you think there are companions. And our particular approach seems to be fairly precise in terms of spatial resolution. This is low-key, which is, again, a sort of PCA-based approach, which works similarly well, I would say. Ours might be a little better, but not much, I would say. Okay, so that's, now, of course, when you're doing this, there were a bunch of things we did sort of there wrong from the modeling point of view. And the approach I just described is quite useful for just trying to find potentially interesting regions where there might possibly be a companion. But as I said, the whole point of doing this direct imaging is to find the spectrum. And in what I just described, we just made some very naive assumption about the spectrum being white. And so what I really wanted to focus on in this talk was basically the problem of trying to estimate the spectra in a more principled way. And as I said previously, we assumed it was white. But the correct thing to do would be to assume that it's unknown and treat the spectrum as just a latent variable in our model that we're going to infer as part of the fitting procedure. So now we're going to explain our observed data with two competing models. One will be the PCA speckle model that I just described, which is fairly straightforward. And the second one is going to be, sorry, this has got clipped, basically will be a model of the planet where the spatial structure is known. That's just the point spread function of the telescope. With a latent spectra. So the sort of intensity, if you like, at each wavelength of that PSF will be an unknown variable that will fit as well. So, so what I'm drawing here essentially is a sort of visualization of this generative model, which is going to have two pieces to it. One which will be essentially the speckle model, and another one which will be the planetary model. Okay, so the speckle model, that PCA model, this is just a graphical model representation of that. So you have a sort of known basis that you've computed beforehand. That's essentially, you've got this held out part of the annulus. You've run PCA on that to construct your basis. And then you have some maybe prior on what the weightings on those basis, ZIs are going to be the weightings on those different basis functions. And then you get the estimate of the speckles by just multiplying Z by W. I'm assuming there is will be some offset, which I'm just removing just to keep the notation straightforward. And you might have some kind of prior on what those what the weightings would be. Maybe they're coming from some sort of zero mean Gaussian prior or something like that. Okay, so this model here will then contribute to explaining the raw data you see in your cube. But then also we're going to have a model for the planet. Okay, so the idea here is that now the shape of the planet, that is the point spread function, is known. But what's going to be unknown is the spectrum. So the idea is that this is also, you can think of this as just a weighting at each wavelength for this planetary shape. That actually will change as a function of wavelength 2, because of course the point spread function is wavelength dependent. And we might have another latent variable, which would be perhaps the position of the planet in each of the exposures I. Okay, that's why there's a superscript I here. And you notice that most of these variables here all have superscript I, but the spectrum doesn't, because the spectrum should be consistent across the different exposures. Okay, and so the idea is that both the planet model on the right and this speckle model on the left, both of these will essentially vie to explain the observed data. That is the raw data cube. And what we're going to do essentially is I'm going to show you a video of basically this model of inference being run in this model, where we present the data Y here, and we're then running inference on the planetary spectrum here and these coefficients Zi. This is the weightings on the speckle noise. And the model also infers the offsets between the exposures, but I'm not going to show you that piece. Okay, so the key point here is that we're jointly fitting both the planet model and the noise model. Okay, so previously we were just fitting the noise model blindly and hoping whatever was left over might have some sort of planetary signal in it. Here we're doing something more principled, which was we're writing down what we believe is a sort of accurate process by which the planetary signal and the noise signal is formed, and then we're just trying to then estimate essentially the weightings of the two components on the data. And the objective function you're actually minimizing, for this particular case, we're basically assuming Gaussian noise and some fairly simple other things. Turns out to actually be sort of quadratic. It is actually constrained quadratic because the planetary spectrum can't be negative, so that these variables S have to be strictly greater than 0, so 0 or greater. So therefore it is actually a constrained convex optimization, so we're guaranteed to get to the same solution. Okay, so what I'm going to show you here now is actually just running inference in this model. Let me just do this for a second and then pause. Okay, so what you're seeing over here, this is the raw 5 raw exposures. I'm just showing you one of these little slices. This is radius here, and this is wavelength here. And so you can see the sort of diagonal structure of the speckles. The little red dashed line is the inferred position of where it thinks the planet is. Here you see the reconstruction from our model. That's the reconstruction of both the planetary signal plus the noise signal. And then in this column here, you see the noise component. And then probably the contrast on the projector is not very good, but this is essentially the planetary model here. So this column plus this column equals this column, which should be close, up to Gaussian noise, to this one here, the observed data. And then in this far column here is the residual, but I think the contrast is too poor on the projector. And what I'm showing at the bottom is the ground truth spectra in blue, I think. Maybe the ground truth spectra is in red, and then the current estimate is in blue. And then what I'm looking at here, I'm just taking a little slice through one of these a scan line, if you like, for one of these little things, and we're showing essentially the planetary contribution in blue, the raw data is in black, and then the noise model is in green. So if you do blue plus green, you get the reconstruction, which is in red. So the red curve should match the black one, and then as we run inference, you'll see that the sort of amount of signal allocated, as it were, to the planet in blue will grow as the two explanations kind of vie with one another to explain the data. Okay, so so there you go. You can see. The red, I guess, is the inferred spectra. So you can see that the two curves are sort of converging. This is a situation where we've inserted a planet with known spectra. Okay, so I know what the answer is, and we're just seeing whether we can reliably recover it. And I picked one here, which I think it's maybe about. The planet is roughly about 5% signal strength compared to the background noise. Okay, so you can see here that when it's done right, you can see that this little bump, which corresponded to the planet, was not explained by the speckle model. It was explained by the planetary signal. Okay, so that you can see that if the blue part plus the green will equal the red, and that fits the data quite nicely. Okay, So the key point here is I think that you want to be sort of thinking about the formation process by which your data is generated, and then hopefully you're able to invert that in some fairly efficient inference scheme. So what you can do is you can then try some synthetic companions on your data and see how well you can actually recover the true spectra. So what we did here was to actually, for the various companions of that star, this HR8799 that I was referring to, we know roughly what the brightnesses of each of the companions are from other instruments. And so you can create synthetic companions of that signal strength and see how well we can and recover them. So what you're looking at here, the black is the ground truth, and then the colored lines show essentially the estimated spectra with error bars. Okay, so in this case here, the companion that was inserted was just a fake one with the same spectrum. Of course, when we do this on the real data, the spectrum will be different for the different companions. So another way of visualizing sort of the performance of the algorithm is just to sort of try and understand here. This is just a radial position, a radius of the companion, and this is the relative brightness compared to the speckles. Okay, so when we're at, say, this row 2, that means the planet signal is about 2% the strength of the actual speckle noise. And so what I've done here is to overlay the positions of and brightnesses of the companions for this particular star. So this gives us a sense of how well the accuracy we might expect basically from our spectra inference on the real data. So this was the results we got. So what you're looking at here is, this is wavelength here on this axis. Each of these there's 4 different rows here, B, C, D, E, corresponding to 4 different companions. This solid black line with error bars is our inferred spectra. And then these are the absorption bands here of different molecules, ammonia, acetylene, carbon dioxide, and methane, and so on. So if you see a dip, that might suggest that that molecule might be present in that planetary atmosphere. Now, of course, how do is there any sort of other validation of these results? Well, it turns out, yes, one of the companions, there was actually a previous publication which, and so that was actually on the longer wavelength end of the relative to the instrument we were using. So the previous work had the sort of dashed spectra you're seeing here, and then our inferred one was this one with the solid line. So they're fairly noisy estimates, but at least some consistency, I would say, between them. This is just for one of the companions of this star. And then let's see, how am I doing for time? Okay, maybe a little bit fast. But. Okay, so then what happened is, this is actually, just to show you that our results, I think we had slightly lower error bars in the end, and it's a bit hard to know precisely. CLIP is one of the other PCA-based methods, which isn't doing this joint inference. They got somewhat similar results to us. Again, it's sort of slightly hard to know which one is actually, really, in some sense, correct or not. Okay, now I wanted to just change gears slightly and describe a different approach that somebody else used. So this is one which actually, one of Bernard Sholkoff, who's a prominent person in machine learning. So he's also quite interested in astronomical applications of machine learning and has done some stuff with David Hogg. So one of his students, Krickelmol, looked at our model and decided that they would try and build a discriminative version of it. Okay, so the model I describe is a generative model, and this is an alternate approach which uses many of the same sort of principles, but it's just, I think it's illustrative how you can attack the same problem using a different sort of machine learning toolbox. So they use the same basic structure. So they were going to use the same representation that we use, the same idea of finding an annulus, and then holding out a portion of the data, and so on. The key difference is that when they were testing this little region in magenta, and they were going to use the region in green as training data. So in our model, we just were fitting this generative model, basically, we would use the green region to train the speckle basis in an unsupervised way. So we're just doing PCA, basically. And then we would run a little generative model on that magenta region to then see how much was contributed to by speckles and how much by a planetary signal. So what they're going to do is something slightly different. Okay, so what they're going to do is to basically build a training set which consists of both positive and negative examples using this held out region. Okay, so what's going to happen is
they're going to take held out region, take a little strip like this, and they're going to, if you're trying to use a discriminative model, you need to have both positive examples and negative examples. Now, we have plenty of negative examples, that is, regions where there's no companion or planet, but we don't have positive examples, at least, very, very few examples of companions that we know are real detections. So what they're going to do, of course, is to fake them, all right? So what they can do is if you have a generative process which you somewhat believe in, you could use that to just generate for you sort of fake positive examples. That is, you could sort of, create a planet, and you can control its spectra and its strength, and then insert it into some, just simply add it in basically into on top of the signal that you have, which is the negative example, which is just, obviously just the speckle noise. And then if you do this, you can build up a big training set here of both positive and negative examples. And of course, to do this, and then what we're going to do is train a classifier to basically separate the two distributions. Okay? Now, to do this, of course, the catch is that when we come to apply this classifier on some new region, we won't know what the spectrum is of the planet. So in this scenario, what you're going to have to do is when you're generating those fake positives, you're going to have to take a whole load of different spectra that you might think might be plausible and generate fake positives, for each different type. Okay? And then hope that somehow the classifier is going to be able to generalize to some, something close to these. Of course, the true spectra of a new companion you're hunting for may not exactly match any of these. You're just hoping the classifier is going to be able to generalize. And of course, you also want to sort of vary the signal strength of the companion that you insert and so on and so forth. And so the idea is then to construct this large training set of real negatives and then sort of these fake positives you've made by synthetically inserting a whole range of different planets. And then, given that labeled training set, you can bring to bear a discriminative learning technique. Now, Bernard is a big fan of SVMs because he was one of the sort of co-inventors or people behind them. So he used an SVM in his particular case. And sorry, my text has been chopped off here. But the point is, I think in this day and age, we would try perhaps to use a deep net for such things. You could easily, this is a point Jitendra actually raised at the end of the last talk. If you have targets, deep learning works really well. And here what you're doing is synthetically constructing a data set where you have known targets. Okay? Whereas the previous thing I was showing you with the generative model, that was just, there were no targets. You were just trying to sort of fit the data by explaining it as best you could. So just to contrast the two models I've been talking about here. So this S4 model I described, basically your data that you're going to use is just the actual sort of background, the raw data of the cube. And our algorithm was really just principal component analysis, which is unsupervised. And at least for the detection case, we're just using the correlation between a residual and a template. You could also use that joint model I described also to do detection, but it's a little bit slow. And that's a point I'll just come to in a second. And then in the discriminative case, what you're doing is now you're sort of creating artificially two different data sets, right? The background data and then the background data plus the inserted planet. And then that way you're turning things into a supervised learning problem, and then you can attack it in their case with support vector machines and so on. And then what you're going to do is just use that SVM to then examine a new patch and just say whether you think there's a planet there or not. So just to sort of take this one point further, I guess, or just to make this clear. So in the first part of the talk, I was really talking about fitting a generative model to data. Okay, so the more interesting one there is when we had a sort of joint fit of both the planet and the noise. And the catch is you're going to have to do this you have to, if you have, in our case, we're very lucky. We were able to build a model in which inference was fairly easy. Okay, so it was a quadratic, so it was a convex optimization problem and well behaved. But it is quite slow to run. And if you had to run this at every location in a giant data set, it might be very painful. Another way you could use the generative model, and this is really how was used in this discriminative variant, is you're basically going to use a generative model as a way to generate sort of data with known targets. So in the previous example, it was just planet, no planet. But you could imagine generating things where the target now is just this, a vector describing the spectra. Okay? And you could then train instead of just a simple classifier, you could train a regression function, possibly some kind of deep net, to go directly from the raw test region to a series of numbers that would characterize the spectra. And I guess if they're all 0, then you would say there was no planet.
And so why would you want to do this? Well, you know, the point being, in some sense, what you're doing there is building kind of a quick approximator to the model, the actual generative model that we just talked about earlier. And those, I think there's clear wins if you, in terms of speed. So that is, if you had a very large, you know, data sets you want to hunt for, you know, or for companions. So you know, you have lots of positions and you want to hunt for. Then you have the advantage is that once you train this discriminative model, it can be run pretty quickly, right? You're just simply plugging in a raw data cube, and you just do a series. There's no optimization or anything like that. It's just a series of, you know, matrix multiplications and a few other things like that if you're using a deep net, and you get out at the end of the network some prediction as to the spectra. So no, I mean, I'm not aware of anyone who's actually done this, at least for the you know, the exoplanet spectra problem. But this is, I think, is a very viable sort of way of thinking about using generative models in combination with deep learning approaches. Okay, so just to summarize, I guess I talked a little bit here about a sort of generative model for fitting planet spectra with spectral cubes. I think what was interesting about it was the fact you were sort of doing this joint fit of things, and I haven't seen that done in these other methods that people use for looking at exoplanet data. And as I said, as I've just been saying, I think there's very interesting ways you could combine your generative modeling with some deep discriminative approach as well. And from a sort of practical astronomical point of view, I think it would be interesting to try these techniques on some of the new data that's come out. So this Gemini Planet Imager has much better resolution and contrast than the P1640 instrument. And so they have some pretty interesting results that came out, you know, sort of, you know, recently on that same star system, in fact. And the optics, the optical train in this Gemini Planet Imager is actually very similar to the P1640. So the noise artifacts have very similar properties. So I think a lot of the methods I've been talking about here, we should actually generalize fairly effectively to this instrument as well.